Okay, so you're familiar with series, right? Series have like a lot of applications that we can basically do, and one of them you can basically think about them on your own. Let's say, for example, you have like something like this. Let's say you have 3x minus 7 to the power of 8, and you want to like expand this. In fact, let's just make it to a power of 4 so the video doesn't take that long. So let's say we have something like this. Normally we use the binomial theorem to just kind of like expand this and see the coefficients and how they work, but basically it's just that we can like rewrite this in some sort of like a series there. Notice that we can rewrite this, since it's to the power of 4, we expect that the highest degree will technically be of 4. So we expect that we'll have like some constant and some x term probably, and some x squared term, and some x cubed term, and some x4 term, because x of 4, that will be the last term there. So we have c4 x4. So all we know is that we can express this in terms of this one. But now notice something. If you plug in 0 here, what happens? You end up with 7 to the power of 4. That's a big number. Let's use 2 instead. So we'll end up with a 2 to the power of 4. That gives us 16. Notice that if we plug in 0 here, we'll have 16. That's minus 2 to the power of 4, which will just be 2 to the power of 4, and that will be 16. And notice that if you plug in 0, every term here goes to 0 except c naught. So we can rewrite that c naught is just technically equals to 16. Now let's continue and do something weird here. Let's take the derivative of this thing. If you take the derivative of that thing, we'll just have 4 goes down. The derivative of the inside is 3, and we just subtract 1 from there, and then we just have a cube there. So we have something like that. And if you take the derivative of this, we can also take the derivative of that. The derivative of c naught is just 0, and then you just have c1 plus 2c2 x plus 3c3 x squared plus 4c for x cubed. If we plug in 0 again here, notice something. We'll end up with minus 2 to the power of 3. We'll end up with minus 2 to the power of 3, which is just negative 8. And here we have 4 by 3, which is 12. And 12 by 8 probably gives us about 96. So we'll have negative 96 there. And if we plug in 0, every term here goes to 0. Then we just get that C1 is technically equals to negative 96. Okay? Let's continue and see what happens. If we take the derivative of this, notice that we have 12. This number here is just 12, right? And then if we multiply that by 3, we end up with 36. The derivative of the inside is 3, and we'll just have 3x minus 2, and you just square that. If you take the derivative of this one, here we're just going to end up with like 2c2 plus the derivative of this one will be 6c3x plus 12c4x squared. If you plug in 0 again, what happens here? If you plug in 0 here, what happens is that you have negative 2 squared, which is just going to give us 4. 4 by 3, it's 12. 12 by 36, it's, let's see, 12 by 36. This is the same as just 10 by 36 plus 2 by 36. 2 by 36, that's 72. And 10 by 36, you just add 0 at the end, so it's 360. And you just add the 2, and then you get 2, and 6 plus 7, that gives us 13. And then we have 3, and then we have 1 plus 3, that will be 432. So here we just get 432. So now let's look what happens here. You have 432. That's when you plug 0. That means you must also plug 0 on this side. Then we have that 432 is just equals to 2c2, because here this will be zeros right there. Okay, so let's continue and see what happens. Now you want to divide this one by 2. You want to divide this one by 2. Then c2 will be, here we have 400 divided by 2. That will be 200. That will be 200. And then what happens is that you have 32 divided by 2. What's 32 divided by 2? That's just going to give us 16. So we expect that that will just be 216 there. Okay, then we can do this for C3, C4, and just get the coefficients of that. But basically what I'm doing here is that I'm showing you that if you just write the series expansion of this, you can basically express this in terms of like, you can basically find the coefficients. You can do the same thing using the binomial there, the binomial theorem there. But here I'm just showing you this key size idea of what's happening here. So that means that 3x minus 2 to the power of 4 is basically equals to c naught, we got that is 16. So plus c1, we got that as negative 96. So that will just be a negative 96x. And we go on and continue and we end up with C2 being 216, so plus 216 x squared. And then similarly you can do the same process and get that the C3 and C4 there, x to the fourth, and that will be basically the expansion of that. So are we limited to only polynomials? No, basically you can also do this on e to the power of x. So but with e to the power of x, notice that this is not a polynomial like this one was. This one, it was easy to spot that the last term will contain x to the fourth. Because it's a polynomial there, you can basically just say x to the fourth, and that will be your last power of x there. So it's a polynomial of degree 4. Then with e to the x, it's not a polynomial, but we can do the same thing basically and say c naught plus c1x plus c2x squared plus c3x cubed plus, and we go on up until infinity, because this is not a polynomial, so we'll have an infinite number of terms that can basically express that. Notice something here. With e to the power of x, if you plug in 0 here, e to the power of x becomes 1. And if you plug in 0, every x term here is just going to be 0. Then we end up with that c naught is just technically equals to 1. What happens if you take the derivative of e to the x? It remains the same. But now notice that c naught goes, if you take the derivative of that, and you're just going to have c1 plus the derivative of this one will be 2c2x plus the derivative of this one will be 3c3x square, and plus you have c4x4 there, that will be 4c4x cubed, and then you just go on and do that infinite number of derivatives there. Then if you plug in 0 here, you have 1. If you plug in 0, you have 1. So that means basically that we get c1 equals to 1, because every x term here is just basically going to be 0. And we can go on and derive for the third time, and then we have the derivative of e still remains this. Derivative of e to the x still remains the same there, and we basically have this derivative of this one will be 0, and then we take the derivative of this one, which will just be 2c2, plus the derivative of this one will be 6c3x, plus the derivative of this one will just be 12c4x squared, and you continue that number of derivatives. And now notice if you plug in 0 here, you end up with 1, and if you plug in 0, every time goes to 0 except for 2c2, and then you end up with that c2 is basically equals to a half. We can do this for c3 as well. The derivative of e to the x for the fourth time now just goes to e to the x, still remains the same. And if you take the derivative of that one, for the third time now, the derivative of this one will be 6c3 plus 24 c4 x plus that number of many derivatives of that. Notice that if you plug in 0 here, every term here with x goes to 0, and you'll just be left with 6c3, and e to the 0 is just 1, and then you get that c3 is basically equals to 1 over 6. 1 over 6. But now notice something here. c1 equals 1, c2 equals 1 over 2, c3 equals 1 over 6. Do you see any pattern here? Do you see any pattern here? If we take the fourth derivative, notice that we'll have 2 by 12, which is 24. So we expect that c4 will give us 1 over 24. So in a way, e to the x is basically equals to 1 plus this one goes with x. So we just have a 1x, which is just x, and this one goes with x squared, and this one goes with x cubed, plus, and this one will go with x to the fourth, and we can do this a number of times. We can do that a number of times. And in a sense, notice that here we have like an infinite number of terms there. They're just going to keep progressing like that. But notice a pattern here. We can find a pattern of what's happening here. Notice that the first term doesn't contain x. So we can just say this is x to the 0. This is x to the 1. This is x to the second, x to the third, x to the fourth. So basically we can write this as a summation. Since we have an infinite number of terms for this one, then we can start basically from 0, and then we'll just have x to the n. So that way we know that the first term will be x to the 0, which just gives us 1. But let's look at these other terms. Here we have a 1 in front of x, here we have a half in front of x, and here we have a half in front of x squared, and here we have a 1/6 in front of x cubed, and 1 over 24 in front of x4. What's the relationship between 24 and 4? We know that 24 is just 4 factorial. What's the relationship between this 6 and this 3? We know that 6 is equals to 3 factorial. And if you look at this one here, we know that 2 is just basically equals to 2 factorial. So there's a relationship between the coefficient here and this power of n there. So we can do the same. We have a 1 here, we have a 1 factorial, and here since we have an x to the power of 0, that means we have a 0 factorial there, which just gives us 1. So notice that that factorial is under, it's a denominator there. It's below the fraction line. It's a denominator there. So we expect that here we'll just have 1 over n factorial. So this is a series expansion of e to the power of x. We can do this for everything, sine x, cosine x, everything basically. So the procedure is just the same. We do the same procedure throughout. So let's look at another example. Let's say maybe you have, let's look at 1 over x minus 1. In fact, let's say x plus 1. So if we look at this, we want to express this as c naught plus c1x plus c2x squared plus c3x cubed plus c4x4 there, and to infinite number of terms, because it's not a polynomial, then it will consist of infinite amount of terms. Infinite number of terms there. If you plug in 0 here, you have 1 over 1, which is just 1. And if you plug in 0, every x term will be 0 throughout. Then you just end up with c naught equals to 1. If you take the derivative of this one, we just end up with minus 1 over x plus 1 square. If you take the derivative of this side, the derivative of c naught is 0. Then you just end up with c1 plus 2c2x plus 3c3x squared plus 4c4x cubed plus that number of derivatives. You just continue doing the derivatives then. If you plug in 0 here, notice that you end up with minus 1. The derivative of 0 will be minus 1. And if you evaluate this other terms at 0, they'll just go to 0, but you only remain with c1. So c1 will be equals to minus 1, right? And then if you take the other derivative of that, the other derivative will just be, the second derivative of that will just be 2 over x plus 1 cubed. Then we have that. Take the derivative of this one, the derivative of c1 will be 0, and then you're just going to end up with 2c2 plus 6c3x plus 12c4x square, right? Plus, and you're just going to continue doing that. And then now we put in 0, we're just going to end up with 2. The derivative, the second derivative at 0 is 2 here. And notice that if you evaluate this at 0, every x term will go to 0 and you just remain with 2c2. So in a sense, c2 is just basically equals to 1. c2 is basically equals to 1. Okay, now let's take the third derivative of that. You can derive this. I assume we can all do derivatives in our heads at this point because, well, we are familiar with derivatives. So, okay, so now let's derive this. The derivative of that one will just basically be equals to, now we're taking the third derivative, which will just be 6 minus, and then we just have x plus 1 to the 4th. This will be equals to the derivative of this one. This one will just be 0 there, and you're just going to end up with 6c3 plus 24c4x plus, and you're just going to have an infinite number of derivatives there. Okay, and if you evaluate this at 0, we're just going to end up with minus 6. And every x term will be 0 there, and we just have 6c3. And from then, that means that c3 is basically equals to minus 1. But notice, do we have a pattern here? Let's see. C naught is 1, C1 it's minus 1, C2 it's 1, and C3 it's minus 1. So we do have a pattern. This basically alternates between a positive and a negative, and it's just going to progress like that. You can do another derivative just to confirm that. So now let's see. So this means that 1 over x plus 1, this is equals to 1 plus C1 is minus 1, right? So we have minus 1x. That would just be minus x. So let's just you can really put in a negative, doesn't really matter. So, or you can just say minus x, it's fine. And c2 is just equals to 1, and then you just have x squared. And c3 we just found that it's minus 1, and then we have minus 1x cubed, and we're just gonna progress like that. Notice that 1 is even, it's positive. This one 2, the second term, 2 is basically even. This one is odd. The first position is odd. This one is even. This one's odd. This one is even. Wait, what? Okay, let me restart that. First position odd. Second position even. Third position odd. fourth position even. So for every even term, we get a negative coefficient for every even term. But basically, we know that this is 0, right? This is where n equals 0. So let's start from this part here. So if we start counting from here, see 1, it's odd, right? Here it's even, here it's odd. So for every odd n, we expect a negative 1. So that means that we can basically say this is the summation from n equals 0 of x to n. So for every odd 1, we get a negative. If n is 1, we get minus 1. So if n is 2, we get positive 1. And we know that every number squared is basically equals to a positive. Except if we're dealing with a real set of numbers, then yeah, it's positive. Then we basically have something like this, which you can regroup and then just have a summation from, then you just have technically minus x to the power of n. And if you check, this is a geometric series, so the convergence interval of that is basically minus 1, 1. So that's where we can evaluate this series. So we know that 1 over x plus 1 is basically expressed as something like this, or like this, doesn't really matter. So you have something like this, where x is between minus 1 and 1. So right now, I hope you're familiar with our series. So now what we're going to do is we're going to apply series to solve differential equations. So basically what we do is that we say y equals the summation starting from 0 to infinity of Cn xn